Good to see you again here in our second part of the conference. We have now three sessions, two regular sessions, and the third will be short and will bring younger researchers to present us. And it's all going to be till 4 o'clock. So now we are starting with the heavy technical session of secure computing and network. And I would like to invite our first speaker, Professor Yuval Shavitt. Yuval Shavitt is professor of electrical engineering at Tel Aviv University. Before joining Tel Aviv University, he worked for 4 years at the networking center of Bell Labs. In 2004, he incepted the DIMES project for mapping and the internet infrastructure using thousands of lightweight software agents. So please, Yuval Shavitt.
Thank you. Actually, what I want to tell you about today is something that stems from this DIMES project. And I'm going to use the great introduction that Sharon gave us earlier about hijacks. So what am I trying to talk about? So the thing is that when we connect our infrastructure to the internet, we're exposing ourselves to a myriad of attacks. Man-in-the-middle attack is probably one of the most vicious one and the one with the highest consequences. But we also aware of phishing attacks, where one impersonates to your website. We know about espionage attack, people trying to spy on your intellectual property, and there are other things. I'm not going to talk about network DDoS, although it is also something we care about. So the regular mode of operation in the internet still today, although all the peer-to-peer infrastructure that is deployed, is the client-server model. So there's a server, there's a client. The client is issuing a request, and the server is answering the request. What happened in the man-in-the-middle attack is that there's this vicious guy somewhere in Asia that wants to break into the server. To do this, what he's doing is that he managed to somehow trick, I'm going to talk about how, the internet routing infrastructure, so the traffic will go instead of to the server directly through this malicious user. And by doing this, the user can alter the communication, generate new communication link with the server, and posing as the client, and be able to maybe penetrate into the server. There are many kinds of man-in-the-middle attacks. It's not a single type, and this talk is too short to talk about this. But these are really things that people have to be afraid of. The other type of attack is a phishing attack. Here, what we're doing is that just as before, we're getting all the packets destined to some server to our malicious guy, but this time he's answering the client, impersonating his website. This is a great way to, for example, to steal logins and passwords. So I'm impersonating, say, a bank website. People log into the bank, they give their login and password, and then they get some kind of error message, and maintenance come back in 20 minutes. After 20 minutes, everything is back to normal, and I have many accounts, IDs, and passwords to use whenever I want to. Finally, there is espionage attack. Here, what I care about is usually not the server, but the client. So there's a client, and I'm really interested in its intellectual property, and he's going to some server. This server can be an email server, backup server, VoIP server. And again, what I'm doing is that I'm hijacking the traffic. The traffic is flowing through me. Again, I can do downgrade the text in order to terminate the connection at my endpoint and be able to listen to it. Or even if it is encrypted, I can store it, and I have all the time in the world then to try and break the encryption. And finally, there's a network DDoS. I'm going to skip this here. So how do we do route hijacks? So Sharon talked about it in her talk, and I'm going to try and do a more comprehensive review of all this. So the most famous, probably, way of hijacking an IP address is by using BGP. And Sharon showed you one example where I'm sending a BGP announcement that is malicious. I'm giving the wrong destination for this IP address. And by this, I managed to persuade the users to send all their packets towards my destination. For doing this, I have to somehow be a player in the BGP game, and it turns out, as recent history shows, it's not that hard to do. But even if I'm not a player in the BGP game, I'm not an ISP, and I don't have access to ISP, I can also manage to alter BGP announcements en route if they are not encrypted, and be able to change them so that it will benefit my needs. The other popular way of doing this hijack is using the DNS infrastructure. Again, Sharon talked about it. And by changing the record of a DNS server, I can direct the traffic anywhere I want. And documentation of DNS hijacks are various. A lot of them happening every day. The third type of hijack is something that people don't usually realize, because in networking research, people talk a lot about the network control and the network control plane, like DNS and BGP. But there are hijacks that can be done on the data plane. The idea that I take a compromised router, and how do I compromise a router? I can either have a password using somebody from within the organization. Suppose I know somebody works for AT&T operations and they manage to get hybrid. I can guess. I can try and break passwords. I can go into Sony and get their free text files with password ideas. But really, it doesn't matter how do I do this. The minute I have access to a router, and usually it's going to be not a single router, but a group of routers, at the periphery of some ISP, I'm in a position to inject entries to or to change entries in its forwarding tables. And by this, I'm changing direction of traffic without being noticed by the control infrastructure. So BGP tells me that all the packets going in one way, while in fact the forwarding engine is working using different rules. So this is something that by just looking at the control plane of the internet, I cannot detect. And finally, there might be some other ways I'm not even aware of hijacking. So we don't really know what new schemes people will come by to do this task. So what we're looking for is a single solution to cover them all. And here's a suggestion of doing this. And the suggestion is just follow the packets. And following the packets is not as simple as it might look like, but this is the idea. So the idea is we're going to spread many, many agents, thousands of agents. Best thing is maybe if every machine is going to have an agent in it. And these agents going to track the internet routing system by sending traceroute periodically. So we need a way to control all this. So we're going to set up a set of cloud servers. And this cloud server is going to tell each agent where and when to measure. If you're talking about hundreds, thousands, maybe tens of thousands of agents, this can be done on an individual basis. Of course, we need good algorithms to do this. If you're going to grow to millions and tens or even hundreds of millions of agents, mainly every machine is going to have an agent. Then we're going to do this statistically, also based on location and location in the internet. And this cloud server now going to identify problems with routing anomalies, and you can do whatever, with the current cloud infrastructure. You can do multiple layer of anomaly detection and send alerts to customers or to people that are affected by this hijack. And you can also do a root cause analysis of what's happening, because you get the data from multiple sources. You can combine this data with other sources of the control plane, DNS servers, BGP servers, BGP feeds, and get a good picture of what's happening. So what is unique about this type of solution? So first of all, we're talking about large-scale agent distribution, and the real difficulty in the large scale is in the algorithmics, because many of the scheduling and task management problems here, these are problems that we know are NP complete. There's no good solution. There are approximations, and you need to invest a lot in the algorithmics. The other challenge, of course, and this is something that the research community is working on up to these days, is the anomaly detection algorithm. There are many, many good ideas that people are talking about. Basically, the idea is to take the routing data, the delay data, and try to figure out what is malicious and what is not. And I don't have time to talk, but just looking at routing is not enough. You can trick people to believe that everything is okay with the routing, but indeed this is not the case, and you need to also look at the delay. And finally, the idea that if we can do this and we can have a reliable infrastructure, we can also think about automatic reaction to hijack events and automatic correction of the routing infrastructure. I want to show you just one example of, it's not a typical day, but let's say a bad day in the life of a company. So here's a website of a company in Israel. And we set up a system to monitor this company. And look what we've done, what we managed to get in just 2.5 hours. So at some point, these are actually UTC time, this is not Israeli time. We were seeing unreachability of the company from the entire world. So the BGP stopped working. This was not malicious, probably, but still. Nothing was happening. No traffic was coming in for 35 minutes. Things came back to normal. Then 20 minutes later, same thing happening, but now only locally in Japan. The rest of the world looks fine. Things are again going back to normal, and then there is a DNS change. And all the traffic is moved to Amazon Cloud in Holland, in Amsterdam. And this last event was actually, we checked it with the company. This was actually the direction. So this was a DDoS prevention server. So how does this look in the routing infrastructure? So you can see, you start with a regular route. This is a route from Israel to Israel. Only 2 hops in BGP. Then BGP stopped working. What happened? The route expires, but longer routes takes time to expire. So now traffic is going somewhere else. This looks like a real bad hijack event, because now traffic is flowing to a different direction. However, if you wait a little bit longer, you see that no, now everything is shut down. You cannot get out of the source. There is resolution. You can see that there is DNS resolution. And then after a while, things go back to normal. And this is another example of the things from farther away. So this is from Europe. So there's a longer route. And then when the BGP starts working, you see that the route packets are dropped somewhere on the way, in this case in the Amsterdam Exchange. And then eventually, after a few more minutes, traffic is stopped at the source. Example of how does DNS problem looks like. So again, this is from Israel. You can see that all the traffic at some point, going to Amazon in Amsterdam, and then after a while they reverted the traffic back to normal, and you can see they didn't do it well enough. So there was a period of time where there was no DNS resolution. So the change in the DNS server was not perfect, and packet could not flow for a few minutes. And this is the same thing from different. So to summarize, data plane monitoring can really reveal not only BGP and DNS attacks, but also data plane attacks. And the real challenge is managing worldwide agent deployment, large one. And this is something we're working on. If you want to learn more, I'll be happy to talk to you over coffee. That's it.